So far, we've used capital N in the denominator for the population variance and standard deviation. When we have data on everyone in the population. Notice in this case, it's the uppercase N because it's the total population size. Also notice that we have mu in the numerator because we know the population mean because we have data on everyone in the population. We've similarly used N in the denominator in our descriptive statistics version of the variance and standard deviation when we're only describing the data in our sample. Notice in this case, it's a lowercase n because it's the sample size. Also notice that we have x bar in the numerator because we're using the sample average in this case. Now, dividing by n helps from a conceptual level as we start to understand statistics and variability. But we actually rarely use these formula with n in the denominator because they're for situations that, well, rarely apply to what we're actually doing. In a way, you can think of both of these as descriptive statistics. They both just describe data that we have. If we have data on the entire population, sigma and sigma squared describe the variability in the population because we don't have to estimate it. We have all the data. We can calculate it exactly. They are the population parameters. No ifs, ands, or buts. We know exactly what they are in this case. We're just describing them. But in reality, we rarely ever know this. We rarely have data on the entire population. So while we may be very, very interested in sigma and sigma squared, we typically can't calculate them exactly. So this situation rarely applies. On the other hand, uppercase S and S squared describe the variability in our sample. Now remember, they only describe our sample. We can't use them to estimate what that population looks like. But the problem is, that's typically exactly why we're doing the study in the first place. We want to estimate those population parameters like sigma or sigma squared. Descriptive statistics based on our sample limit us to saying things like the average reading score for these 28 kids who received an intervention increased by zero point 0.4 grade levels. But typically, we want to do more than that. We want to be able to say things like, we believe scores will go up for other children in the population if they receive the intervention. Or we want to be able to ask things like, what would be the effect of the intervention in other schools if they tried it? Or maybe ask a question like, what's the effect of poverty on graduation rates across the state or across the nation? Not just what's the effect in this small group of children in our sample. Now, remember, when we talk about estimating population values, we're often talking about knowing whether the things we see in our sample are real in the population. Are they real in the population, or do they just reflect random quirkiness based on the specific individuals who happen to end up in our sample? That's why we do statistics. Consequently, while we can calculate capital S and S squared as a way of strictly describing our sample, rarely do we ever want to just do that. We want more. We don't just want to use the descriptive formula to describe our sample. What we really want to do is use our sample to estimate or infer what the population looks like. In this case, we want to estimate the standard deviation and variance in the population based on our sample. All right, now, This isn't a new idea. We've previously noted the difference between descriptive and inferential statistics, right? Descriptive statistics describe our sample. Inferential statistics are used to make inferences about that population. Okay? Now, with this transition, we've gotten to the point where we are going to leave descriptive statistics behind and jump into inferential statistics with both feet. There is no going back now. So let's start by focusing on the variance. The problem with dividing by n is that if we're estimating the population variance based on our sample data, using the sample size n in the denominator will give you the wrong answer.
I'm sorry, Dave. I'm afraid I can't do that.
You absolutely can't do that. While n in the denominator is okay if you're only describing our sample, the descriptive statistics version, right? Dividing our sample sum of squares by n gives us a biased estimate of the population variance. The value that it gives is a little too small. It underestimates the true value of sigma squared. Instead, we need to use n minus 1 in the denominator. This gives us an unbiased, more accurate estimate of the true population variance based on our sample. And because it's an unbiased, more accurate estimate of the variance, this also provides a better estimate of the standard deviation, which, as we know, is the square root of the variance. Now, because these are estimates of the population standard deviation and the population variance, we don't use sigma and sigma squared, but instead represent them with a lowercase s and s squared. We use a lowercase s in order to make it clear that we're really talking about the inferential statistics formula with n minus 1 in the denominator, right? Not the descriptive statistics formula, which was represented with the uppercase s and had n in the denominator. Now, notice again that we are using a lowercase n in that n minus 1 in order to clarify that we're talking about the number of individuals in a sample, while we use the capital N in the sigma and sigma squared denominators in order to clarify that we're talking about the number of individuals in the population in those formula. Now, because of all this, we should use n minus 1 in the denominator when we calculate the standard deviation and variance. In fact, by default, a lot of software will primarily report, maybe only report, the standard deviation and variance using n minus 1 in the denominator because there's the assumption that's the formula you want. You want the estimate of the population value. So at this point, let me be absolutely clear. Going forward, you should calculate variance based on this sum of squares divided by n minus 1. And you should calculate the standard deviation based on the square root of this sum of squares divided by n minus 1. Right? Now, you may ask yourself, why does dividing by n minus 1 give us a better, more accurate estimate of the population standard deviation and variance than dividing by n does? And there are a few ways you can think about this. One involves how much information is free to vary in a sample once we know the mean. To illustrate this, I'm going to use some of the toys I have scattered around here. Let's say that Mr. Potato Head, C-3PO, takes a test, as does Darth Tater and Yoda. All right? The three of them take a test, and the average is 9. The average across the three of them is a 9. And we know that C3PO scored a 7. And we know Darth Tater scored an 8. What do you think was Yoda's score? Now, think about this for a minute.
I think you know just as well as I do.
Of course. Notice we already know the answer because we know the sample average. Yoda must have scored a 12, right? The sum of their scores must be 3, right? Our sample size times the mean of 9. 3 times 9 is 27, right? C3PO score plus Darth Tater's score add up to 15. So Yoda's score must be a 12. If we know the mean, the final score in a sample is not free to vary. We already know what it must be based on information that we've kind of previously pulled out of the data when we calculated the average. Now, another way of thinking about this comes down to a characteristic of the sum of squares. By its very nature, the sum of squared deviations from the mean of a sample, x bar, will always be smaller than the sum of squared deviations based on the population mean, mu. Unless, of course, mu and x bar happen to be exactly the same values. To see that, let's return to the quiz scores for C3PO, Darth Tater, and Yoda. Here's the distribution of quiz scores, right? The sample mean was 9, so our deviations from the mean are -1, -2, and +3. This works out to a sum of squares of 14. Now, unless we were somehow incredibly lucky, the sample mean won't be exactly equal to the true population average. So let's say the true population mean, mu, is just a little bit different. Let's say the true population mean is 10. In that case, our deviations from the true population mean are -2, -3, and +2. That works out to a sum of squares from the population mean of 17. Notice that our sum of squares based on the sample mean was smaller than when we used the true population mean. And it will always be smaller unless x bar and mu are exactly the same. But even if they're just slightly different, the sum of squares based on our sample will be smaller than the sum of squares if we actually knew the true population average. Now, because it's based on a sample, the sum of squares using the sample mean will be biased towards being too small if we use it to estimate the population variance, right? And because that sum of squares that's biased towards being too small is in the numerator of the variance, if the sum of squares is biased towards being too small, the variance will be biased towards being too small. In that case, you can think of dividing by n-1 instead of n as balancing out that bias. Now, the third and definitive way of looking at this is mathematically. You can show that in order to get an unbiased estimate of the population variance, you must divide by n-1. Let's end with a very quick run through that proof, strictly for your own edification and entertainment. All right?